Today's main seminar, we have Tattwamasi, who will be from University of Potsdam, who will be talking about relative invariant subalgebra rigidity property. Take it away.
Thank you for the invitation. Before I go to the topic, let me give an example of an explicit boundary action, like discussed. So consider free group on two generators. So these are all possible finite words that can be formed out of A and B modular cancellation. Now, what I can do is I can look at the boundary. So how do I define it? So these are all possible infinite words that can be formed from A and B modular cancellation. So infinite reduced. So for example, if I have some word like A inverse, B inverse, B, and so on, then the reduced word is just these guys, they cancel each other out. And so on. So modulo the cancellation, anything that remains, that is my reduced word. And I claim that there is an action of the free group on this space. So you give me an element from the group, you give me an infinite reduced word. There is only one thing I can do. So I put it on the left-hand side of the word W. If there is cancellation, I cancel it. If there is none, I keep it as it is. So this is my action. And this, because this I can see it inside 0, 1 to the power gamma, right? I give it the product topology. So this is a closed compact space. And this action is an action in the sense of as Aaron defined. So this is a homeomorphism. No, just the free group, not the abelian group. B and B don't commute. Because this is an infinite word, so there is no right-hand side. So I can only act it on the left-hand side. And my claim is that this is a boundary action. Sorry? It is strongly proximal and minimal. It is also topologically free, but it's strongly proximal and minimal. So before I go on to prove it, here is an interesting property to keep in mind. So I claim that if you give me an element in the free group, so for any Zin F2 which is not identity, I can find exactly 2 points on this space delta F2 that I defined such that G fixes these points so G of xg plus is xg plus, G of xg minus is xg minus. Moreover, if you give me any other y which is not xg minus, then I can send it to xg plus as n goes to infinity. as long as it is not this other point. So pictorially, what is happening, the picture that Aaron drew is actually very good for us. So this is the Gromov boundary that I defined. And for G, there is a pole here, xg plus. There is a pole here, xg minus. I'm not doing anything to these points, these are fixed. But if you give me any other y here, I can keep on applying the G and just the powers of G, not any other element. And then I keep on sending them and I will reach eventually xg plus. So here is an example. For example, let me pick the word A. So say that G is A. So what are the poles? Exactly, very good. And the other thing is A, right? So XA plus, XG plus is A, and XG minus is A inverse, A inverse, A inverse, and so on. And if you apply A to it, it is not going to do anything to it. It is being fixed. Now, well, Newton element fixes everything. So I don't care about, yeah. Now I claim that if you give me any other y, any other word w, which is not this guy, I can send it to A by the powers of A. So, sorry. It is, yeah, so I just want to make an argument. So if I write this word as W1, W2, Wn, and so on, if it is not this A inverse, at some point n, it will not be A inverse, right? And from that moment onwards, I can just keep on applying A to it and send it to A. Because it's a product topology, I don't care what happens at the end. I only care up to the finite things in the beginning. Okay. Now, this is enough for us to show strong proximality. Because if you give me a probability, so what this guy is, so if you give me a probability measure here, what happens to A to the power n nu as n goes to infinity? Except this point, right? So it's basically a Dirac at this xg plus or xa plus some coefficient plus 1 minus a Dirac at xa minus, just by a dominated convergence theorem, right? But as Aaron said, we need to go to 1 Dirac. Now there is what I do is I now apply B to it, because I know that the poles of B are disjoint from this. So let's apply B to the power m a n nu. Because the poles of B are disjoint from this, so it is going to push everything to Dirac at xb plus, and that's strong proximality. And this thing that I wrote here, this is actually true for any hyperbolic group acting on the Gromov acting on its corresponding Gromov boundary. So all you have to do is just replace this by gamma. So gamma is any hyperbolic group. and this is just the corresponding Gromov boundary, exactly the same argument would show that this is strongly proximal. There's no difference. Okay, now minimality becomes a simpler exercise because so what do I have to do? I have to first, so as Aaron said, I have to show that the orbit this is dense, right? So now you pick an arbitrary W tilde. So I have to show that I can get very, very close to this guy by element sub G, right? So what I do is I take Gn to be W1 tilde, W2 tilde, Wn tilde, some Hn, right? You pick any W such that Hn is not equal to W1 inverse. Because I don't want the cancellation to happen at the first place. And then as n goes to infinity, this guy is going to be very, very, I mean, the wards are going to be equal for the first any number of times that you want. And that's minimality. So, I mean, another way of defining the Furstenberg boundaries, if you know Hamana's injective envelope and so on. So this is actually a theorem of Karantar Kennedy that the gamma injective envelope of C is C delta F gamma. If I have time, I'll come back to it. But this is another way of defining the Furstenberg boundary. If you have any questions, feel free to stop me. Okay. So now I'll come back to my original talk. So Aaron did most of the groundwork for me. So I'll just start. So gamma is a countable discrete group for me. And I'm pretty much interested in either looking at the reduced group C-star algebra or the group von Neumann algebra. And I'm interested in studying these objects. So in particular, I ask the following question. Let's say I pick from here a C-star unital C-star subalgebra. I want to know, so does it come from a group? In particular, I want to know if is A going to be the reduced group C-star algebra of H for some H. From some subgroup. Or I can also ask the same question for a group von Neumann algebra. So in particular, I want to understand if the subgroups of the group gamma are somehow, how big is the collection. Now here's an example to keep in mind. So again, I'm in the free group. And consider an automorphism sigma that sends A to B and B to A. And I want to look at the reduced group C star algebra of F2, because once I have an automorphism of the group, it induces an automorphism on the reduced group C star algebra, just by the same canonical way, right? So maybe I say here, so sigma automatically induces a map from here to here. The sigma of lambda z is just lambda of sigma z. And then this guy is all those guys which are fixed under sigma. So maybe I write here. The fixed points. Now here is an example. Here's a question. I claim that this thing cannot come from any subgroup. So why is that?
Subgroup would be either just all of the A's or all of the B's, right? And then it cannot be closed under this.
Yeah, because one group element cannot exist by itself, because it has to be fixed point and no other element in the free group is fixed by this automorphism. So see, this fixed point subalgebra is not of the form CR star H for any subgroup. So therefore, this means that the question that I asked in the beginning, I have to put some conditions on it, on the subalgebra that I pick. I cannot just randomly pick a subalgebra and say that it will come from a subgroup. So I have to put some invariant, some condition. And it turns out that this invariance condition is the natural one to put. So maybe I make a definition. So a subalgebra here is called invariant of free group. Gamma is called gamma invariant if lambda g a lambda g star is again in A for every element in A and every group element. So think of it as a non-commutative analog of a normal subgroup. So if you have a normal subgroup of the group, if you do the conjugation, it remains inside the normal subgroup again. And that's exactly what I'm asking for here, except I want conjugation by the unitaries because I'm inside B of L2 gamma. So then this question that I asked in the beginning, this question boils down to asking, so, okay, like I said, here's an example. You look at CR star of N, where N is a normal subgroup. So this is an invariant subalgebra because N is invariant under conjugation, lambda is a unitary representation, everything is preserved. So this is invariant. So then my question becomes, So there is no other invariant subalgebra inside the reduced group C-star algebra except the canonical ones that come from the normal subgroup. Can this happen? This is the question that I'm asking. Of course, I can ask the question in the von Neumann algebraic setup as well. So when I say subalgebras, I mean here unital C-star subalgebras and here all von Neumann subalgebras. Okay, this is the first question that I'm asking. Now, so this is the invariant. So if this happens, so maybe I make a definition just to connect it to my title. Gamma has invariant subalgebra rigidity property if B has a positive answer. So the answer to the question B is yes. So gamma has invariant subalgebra rigidity property if every gamma invariant subalgebra of L gamma comes from a normal subgroup. And then B gamma has C star ISR property if, as you can guess, A. So this is A tilde, B tilde. Yeah, so I changed them somewhere. But you get it. A has a positive answer. Okay, so this is where my title invariant subalgebra rigidity property comes from. But why I'm asking for relativity? So as Aaron said, so this is here is an important result of Brelard. Okay. Kalantar, Kennedy and Ozawa, that if gamma is a C-star simple group, so if CR star, assume that CR star gamma is simple, and N is a normal subgroup of my group gamma, then CR star N is also simple. So C-star simplicity passes down to normal subgroups. So this is what they proved. So this is true in C-star simple category as well. And of course, on the other side of the world, there are amenable groups, right? So, for example, free group was very far from being amenable. Then we have these integers, solvable groups. And so on. This just means that the reduced group C-star algebra is not simple. You have many ideals. And then here also, normality, amenability passes. To any subgroup. So in particular, it passes to normal subgroups. So normal subgroups inherit both C-star simplicity and amenability property. So therefore I ask, this is the second question I ask. is this property relative in the sense that suppose that gamma has invariant subalgebra rigidity property. Does it pass to normal subgroups? So in particular, I pick n a normal subgroup of my group gamma which is non-trivial, and I pick A which is n invariant. Does this imply that A itself must come from a subgroup? Which is a much stronger question than the original question that I asked. So instead of being invariant under the group elements, I am asking is it just invariant under some normal subgroup, which is non-trivial. Is it enough to conclude that it must come from a subgroup? Okay, so it turns out this question has a positive answer for a very big class of groups. So let me trace back history a bit and say why people started to study this invariance and so on. So this is the theorem of Kalantar with Nikos. And this is where all this thing started. So what they showed is that they wanted to show something, but at the end of the day, they proved a very stronger result. They showed that take gamma to be SLNG, n bigger than equal to 3, and the center is trivial. Then gamma has ISR property. Which means that you look at L of SLNG, the group von Neumann algebra SLNG, and you pick an invariant subalgebra, then it must come from a normal subgroup. So there are no other non-trivial invariant subalgebras there except the canonical ones that come from normal subgroups.
The trivial center is automatic, please, or is an extra hypothesis?
It's an extra hypothesis, yeah. I mean, you can look at PSLNG, just modding out by the center, and the result still holds. And the proof at that point in time involved very powerful techniques of non-commutative Butones-Hudaya and so on. I'll come back to the modified proof technique, which is a bit easier. But this was a very substantial result in the sense that it is basically showing that these guys are all the invariant ones, and it's just somehow surprising in that sense. But maybe not so surprising because in SLNG, to start out with, there are not many normal subgroups because of Margulis's normal subgroup theorem. You know that all the normal subgroups are of finite index. So maybe this is not so surprising for these SLNG things. So now question is this true for the free group where there are many normal subgroups? Like every group is a quotient of the free group just by the construction. And it turns out that this is also true for the free group. And this is what we showed with Yongle. Even for hyperbolic groups, so if you take gamma to be a torsion-free hyperbolic group, then gamma has ISR property. Yeah. Yes. So I asked two questions. So this is A and this is B. So you can ask the same question for the reduced group system algebra as well. So here I'm asking you pick M inside L gamma, which is an invariant. Does it come from a subgroup? And here I'm asking for the reduced group system algebra. Hi, sir. Okay, so and then the natural question for us was to investigate if for the free group, if I can answer this question, that I pick either in the group von Neumann algebra or the reduced group system algebra something which is invariant with respect to a normal subgroup, does it come from a subgroup itself? It turns out that this question also has a positive answer, and this is what I showed recently, that if we take gamma to be a torsion free hyperbolic group, and n to be any normal subgroup that you like, n is not invariant, not trivial, sorry, then every n invariant subalgebra is L of H for some subgroup. And similarly, every n invariant C star subalgebra is CR star H. So being invariant with respect to some non-trivial normal subgroup is enough to see this kind of rigidity property.
Did you say if you have non-examples?
Yes, yes. So for example, maybe I write here. So even for this thing, so one can consider, say for example, F2 times F2. This is the product of the groups, and take n to be 1, the first copy. And then I look at the same example that I constructed, the fixed points. So take A to be the fixed point under the other guy. So C now this is invariant because this guy acts on it trivially. This is invariant because the group is acting trivially here, but this does not come from a normal subgroup. This doesn't come from any subgroup. So this can be done much more generally. Of course, you just have to find a non-trivial automorphism, and the same example works. So the main point in all these examples is that if you take a normal subgroup of the free group, then you can actually show using this boundary construction that we did here that the centralizer is trivial. That all those elements that commute with things from n, this is trivial. But this does not happen here because the centralizer of n is the other copy of the free group. And this is an obstruction to this principle. Okay, so here is another example to keep in mind. Is that okay? So let's consider a free group F2, and let's pick two normal subgroups here. So a priori we do not know that they are going to be disjoint or not, but I claim that this intersection is not trivial. This intersection is pretty big inside the free group. Now why is that? Okay, so pick any G in N1 and any H in N2 and look at GH, G inverse, H inverse, the commutator. Because N1 is normal, this guy, sorry, N2 is normal, so this guy is in N2. This is of course in N2, so this product is in N2. Now if you look at from here, because N1 is normal, this is in N1 and this is in N1. So this product is always going to be inside N1 intersection N2. And this is non-trivial because in free group you don't have cancellations. So this is an important principle that goes inside the proof of all these things, that the normal subgroups. If you take, I mean, this also happens in hyperbolic groups torsion free, that if you pick any two non-trivial normal subgroups, then their intersection is going to be pretty big. It's never going to be trivial. And exactly this does not happen here because I could pick the first copy of the free group and I could pick the second copy of the free group and their intersection is trivial. Okay, so and what goes into the proof of these results is exactly this phenomenon that I gave in the beginning, that you have this north pole south pole property, that this thing here is called north pole south pole property. And if you think about the proof, how the proof goes, so there is one thing that I can do. There's only one thing that anyone can do, for example. So you pick a subalgebra and you want to show that it comes from a subgroup. So what are the possibilities? So you want to show that you pick an arbitrary element A and you write its Fourier series expansion. Right? And what you want to show is that any group that appears here in the Fourier series expansion, so if Cg is not equal to 0, then lambda g itself must be in A, right? Because if it comes from a subgroup, it has to satisfy this property.
It's not there when you do GNH.
You have to be careful to commute, right? Because then that would be the identity.
But I mean, in the free group, they cannot commute.
You can have surely have two elements which do commute.
Uh,
AB, D, and
I guess G is H squared.
exactly.
but I mean,
But they can be different and they can still.
yeah, sure. I mean, of course, you have to pick G and S such that they're not in the cyclic subgroups of each other, but like intersection of G and cyclic sub. Okay. So what I mean is that
That's the only case in which they commute.
yeah. So you want this intersection, this to be identity. That's the only possibility. Okay, so as I was saying, so the only thing that I need to show is that if the Fourier coefficient here is non-zero, then lambda g must be in A. And so what I basically have to do is I have to extract this group part from this Fourier series expansion. And if you recall, we have these canonical conditional expectations. This is true for every group element that sends H here to itself if H in here, so 0 if H is not here. And then using this north pole south pole property, what you actually show is that EG of A is contained inside A. So A is preserved under this canonical conditional expectations. And then it just becomes a trivial algebra to conclude the result from there. So now let me, in the last 15 minutes, talk about, so this type of dynamics is very specific to the hyperbolic groups. So it does not happen for the SLNG, for example. So how does one prove such a thing for SLNG? So here is a very nice observation that Jonglei came up with along with Zhao and also used in Dudko-Jiang's paper. So you pick any subalgebra inside the group von Neumann algebra, L gamma. Now you have a canonical projection back onto it. Because this is a von Neumann algebra, this is a finite von Neumann algebra, so every subalgebra is in the image of a conditional expectation. So using this, you can associate a map on the group. And this is defined using the trace and the conditional expectation. I should say lambda z here. So this is a priori just a map on the group. It has no relationship with the von Neumann algebra that I started out with. But it turns out that this map actually determines this von Neumann subalgebra, because it turns out that this map is a positive definite function. Which means that it takes identity to identity, and it's positive definite associated with any finite collection. So for any G1, G2, Gn and C1, C2, Cn complex numbers, this thing is going to be positive. And the thing that goes into the proof of SLNG is this property called character decomposition. And additionally, okay, so additionally, phi m is called a character. If it is invariant, in the sense that phi m of H, G, H inverse is phi m of H for every G. So when you conjugate it, it does not see the difference. Sorry, G. So and this happens if and only if M is invariant. And what they proved is that if gamma is SLNG and n is bigger than or equal to 3, and you have two pi and psi, which are characters, and their pointwise product, so phi z times psi z is Dirac at G for every G, then this implies that phi is either Dirac or psi is either Dirac. So if you think about this example that I gave here, F2 times E. So for example, if I take the other copy, so let's say this is N1, and let's take N2 to be identity times the free group. Now corresponding to these two normal subgroup, I can associate a positive definite function, chi N1, right, which just takes 1 if it is an N1, 0 otherwise. Similarly here. So the point-wise multiplication of these guys is Dirac. But none of them, but these are not Dirac. So this character decomposition property does not hold in this example. So this is a very strong property. And then using this property, they prove that this is another way of proving it. So this is a theorem of Jiang-Dutko that if gamma has character decomposition property, then gamma has ISR property. And then one can modify their theorem to prove the following relative version. So take gamma to be SLNG, n bigger than equal to 3, the center is trivial. Then gamma has a relative ISR property.
These are for the von Neumann.
No, for the von Neumann case. So I don't know how to prove it for the C-star case. So for example, I even don't know how to prove that. So this is an interesting question in its own right. So take gamma to be SLNG, n bigger than equal to 3. Pick A here, which is a gamma invariant unital C-star subalgebra. Is A of the form the reduced group C-star algebra of N or some normal subgroup. I even do not know if A is simple to start out with. So that would be a good question to answer to begin with. So I'll stop here. Thank you for listening to me.
Right. So I guess you could ask the same sorts of questions for cross products. If you have gamma, do you know anything about this?
So here is a question which we do not know an answer to, and it has never been studied before. So consider, I don't know, reduce, if you consider C-star or von Neumann, it doesn't matter. So say you have M cross gamma, and even you can look at tracial von Neumann algebras with the cross product. and you have the canonical conditional expectation here to M, right? Now I pick N here, which is a gamma invariant von Neumann subalgebra. Assume E of N is C, in the sense that the canonical expectation takes it to C. Does this imply that N is already inside L gamma? In the sense that N does not see any piece of this other side. We do not know how to answer this yet. I think this is the first starting point. And once you have that, then you can go on to build on it.
Questions for Tattwamasi?
Yeah, I was just wondering if you're the OM here and also this one code, if it applies just to SO and Z or to all these surfaces satisfying this marvelous.
Yeah, all lattices satisfying the Margulis normal subgroup theorem. They exactly.
Any other? Yep.
Maybe you already said something about this and my brain was elsewhere, but when you were talking about the hyperbolic groups, you said they had to be torsion free. Is it clear that torsion an obstruction?
Torsion is not an obstruction.
It's not an obstruction.
So it's just that my
hard to
methods,
handle.
my methods cannot handle it.
Okay.
Because if they is torsion, then they do not have this property, and then I do not know what to do with that.
And then I have another question, which is kind of unrelated, but related, which I was thinking of based on the stuff you were talking about in Warsaw. If you have can you use these methods maybe to say that if you have a C-star subalgebra or von Neumann subalgebra that's close to something that's coming from a subgroup, then it also has to come to us from a subgroup?
Yes. So there is a notion. So there is a notion of boomerang. Boomerang property. So it is motivated by the dynamics. So say you have an action on a space, and you pick a point x naught in X, and you want to know how often the group returns back to a neighborhood around x naught. So you keep on acting on x naught, and then you want to know if it comes back to this neighborhood infinitely often or not. And this is what is called a recurrent point. So x naught is called a recurrent point if for every neighborhood U containing x naught, there exists some n naught. So maybe I fix S in gamma, such that S to the power n naught x naught is again in U. So you keep on like making your neighborhood smaller and smaller, and then you know that along the orbit you will keep coming back to x naught. It's called a recurrent point. So this is a new definition. So definition, this is by Glassner and Lederle. So you have a natural action of the group gamma and sub gamma. This is just the conjugation action. You say that H is boomerang if for every S in gamma, you have some subsequence of natural numbers, of course, depending on S, such that S to the power nh, S to the power minus ni converges to H. This is in the Cha body topology. In other words, H is a recurrent point under this action. And examples: normal subgroups, any finite index subgroup, and even you can take a probability measure on here, invariant, like Aaron said, they'll be supported on boomerang subgroups by Poincare recurrence theorem. So now you can define a similar version here as well in the group von Neumann algebra case. So M in L gamma is boomerang if the same thing happens. So if for every S you have a sequence such that you keep on conjugating them and it converges. You have to take the appropriate topology, though this is the Frost-Maré sub. So you get closer and closer to the same under the conjugation action. And you can prove that if gamma is hyperbolic, then every boomerang M is actually L of H. Even if you get closer, you can still show that it comes from a subgroup. It's because topology, yeah.
Did you speak about the stuff last time?
Yes, yes.
Any other questions? Maybe from the online audience? If not, then let us thank Tattwamasi again. And I'll see you all next week.